Think forward. Think Research Channel.
What a multitude. It's glad to have you here. I want to talk about one of my favorite subjects, which is cryptography. And I'll tell you a little bit about what to expect. Okay, first of all, I'll talk a little bit about, this is going to be a mathematics talk as much as possible without mathematics. Okay, so it's designed to offend as few as possible, I guess you might say. First, I'll talk about arithmetic and counting, and we'll talk a little bit about what is cryptography. We'll demonstrate this with something I call the one suitcase, two locks protocol. And then we'll talk about such technical terms as plain text, ciphertext, there should be a T after the X, and key. Keeping track of your keys, which is a real difficulty in this business, and a way to keep track of them, which has been now called public key cryptography, and then another demonstration, which is something called chocolate key cryptography. Okay, so that's what to expect. Now, you might not get that, but that's what to expect. So you're going to have to keep track, Dr. Papillon. All right, I'm a mathematician, and I want to tell you a little bit about some of the mathematics that I rejoice in. And one of those areas is called combinatorics, which is the art and science of counting. Now, you wouldn't think there's any such a big deal as counting, but you count arrangements, and you describe arrangements, and you optimize. You talk about how many ways can you do something, is there a way to do something, and what's the best way to do something. And these are all part of the area known as combinatorics. Combinatorics is part of an area of mathematics that's known as discrete mathematics, which talks about discrete mathematics as opposed to continuous, not indiscrete. We'll talk about that in a minute. Okay. Now, one of the lovely applications of this area, and my other favorite area, which I'll mention in a minute, is to computer security. And what I want to show you right now is a picture. I love pictures. And this is a picture of some of the issues that are involved with computer security. If you have a computer network, all sorts of issues intertwine with each other. You want to be secure, but you want to have access, and you want to make sure that people don't get into websites unless they have a need to, but you want to protect your privacy, but you want people to get a hold of you, and you want to have protection from hackers and prosecution, criminal action, and other ugly things. The university will find out something awful about you and make you stand up and give a talk, or who knows. But there are all these other issues down here: the First Amendment, Freedom of Information Act, National Security Act, Homeland Security. You could, lots and lots of issues that we grapple with networks and computer security. And it's a big problem. How do you keep networks, computers, and information secure? Well, it's called cryptography. Actually, this is not a PowerPoint presentation. Sometimes I think that's a triumph of form over content, but what do I know? So let's make it a PowerPoint presentation. Ready? This funny noises, it's cryptography, hidden writing. That's literally what it means. Kryptos means hidden, I think, and graphy means writing. Is that right, Dr. Papillon? It's Greek. Yeah, thank you. Okay. I didn't remember the Greek for it. I would surely have gotten the accents wrong. Okay. So what do you do? Cryptography is the science of safeguarding information, safeguarding computers, safeguarding networks. And this is all done in a way that you're trying to disguise things. You're not out in the open. So I think maybe we should call this discrete mathematics. Shh, don't tell anyone. Okay. Now this is something that I do in the summer. I go off and work for an agency that does not have a name, to do work that I'm not cleared to know about, for projects that are impossible to solve, and yet they still pay me real dollars so far. Anyway, that's discrete mathematics. Now, the mathematics that I want to talk about actually that is involved in this business is even simpler than that. It's what I call, technically it's called number theory. Now, number theory sounds kind of scary, so I'll just tell you what it really is. It's this. It's arithmetic. This is the most difficult math we're going to do. Okay? The most difficult. And so what I want to do now is I want to tell you what sort of things you can do with arithmetic in computer and network security. And here's what they are. All right. You can verify someone's identity. For example, someone sends you an email. They can sign the message in such a way that you know it comes from them. You can verify that a message has not been altered. That's kind of dangerous. You know, someone sends you a message saying, come at 6 o'clock. One of them mean boys in town changes it to say, come at 10. You show up at 10, oh boy, you're in trouble. You can verify that a message comes from the one who signs it. Darling, I love you. Signed. Well, you know, you can imagine, but it was really from somebody else, and that was a bad mistake. Someone was trying to fool you. You know, people do that. These are rather benign tricks I'm mentioning, but of course, the real hard tricks, the nasty tricks are hackers, stealing your identity, identity theft, a lot of these things. And this is very important stuff to do. You can have, and here's one we're going to talk about a little bit, you can have a secret conversation with someone even if you don't trust them, using arithmetic. And anyone can send you a message that only you can read, and you can prove that you know a secret without having to tell the secret. That's always nice. I know this secret. You know, well, what is it? I'm not going to tell you. Well, prove it. Well, there are ways to do this using simple arithmetic. Okay. Now, all this talk is very well and good, but let's see how it works. Okay? Now, this is what I call the one lock, one suitcase, two locks protocol. That's where we are right now. Okay? And so I need a volunteer who's going to send me a secret message. Aha. Mr. Shapiro. Okay, now, here is how this works. Okay? You have something to write with? I don't. You're pitiful. Here. Okay. Now, this is a suitcase, and it's going to have to be, we're going to do a simulation. And the two locks are these two lovely colors of ribbon that I got from the florist downtown for 58 cents. And one of you, now Brad, you get to choose the color.
Let's go with the maroon.
All right, so I'll take the orange. Now, how this is going to work is Brad is going to write a secret message on that card. Do it. Secret message. Write something down. We don't have all day. He's a good boy, but, you know, he needs mentoring. Okay. Now, what you're going to do with this is you're going to take that message and put it in this bag, and then you're going to zip it up. We're going to zip it up, and you're going to lock it with your lock.
I'm going to
Yes, you're going to tie that around there and lock it. Now, ladies and gentlemen, he has now locked the suitcase with his lock. He's the only one who can open that right now, right? Okay. So now you're going to send it to me. Don't make it too complicated. You're going to have to take it off later. Okay? One lock. I can't open it. Charles can't open it. Mark can't open it. Tom can't open it. I can't open it. Nobody can open it. Well, yes, Brad can open it. Now, I'm going to put my lock on it. And guess what? Now, who can open it? Who can open it? Nobody. Okay, now, I'm going to give it back to Brad. He's going to, first of all, he's going to give me my pen.
There you go.
You got to watch these students. And he's going to take his lock off because he knows how to take his lock off. He knows how to remove it. And there he goes. And now he can hand it to me. And now I can get this lock open because now I can open this and I can read the message. Now notice what has happened here is that he has sent me a message, and it's done in such a way that each of us has our own key. Each of us has our own lock. Now symbolically, on the computer, the lock would be replaced by a hard arithmetic problem that only you know how to solve. And I'll give you an example of that in a minute. But now I can open it and I can read the message. And the message is, bald men are sexy. Hey. Is that what you wrote?
No, that's not what I wrote.
That's not what you wrote. It got corrupted. You got to be careful. You have to encrypt. Now, very careful. You have to be careful of these things. So this is a good protocol. He sent me a message. I was the only one who could receive it because I put the lock on and he took his lock off. But something happened. You have to trust the person at the other end to say Antarctica doesn't exist, which was the message that he sent. I made the other one up, even though it's certainly a bald truth. Okay. So let's talk now about encryption, how it's done. All right? Now, we're going to encrypt a message. All right? Here's the message. The message is Hokies. This is the message that Dr. Steger is sending to somebody who asked him the question, who is your favorite mascot? And it's going to be encrypted, okay? Now, it's going to be Hokies, right. All right, so now how do we encrypt this? Well, here's one way, and it just uses arithmetic. You take the letters of the alphabet, and I convert the letters into numbers. So H is the 8th letter of the alphabet, so I call it 08. And O is the 15th, and K is the 11th, and I is the 9th, and E is the 5th, and S is the 19th. So I write out those numbers. I have now converted a word into a string of numbers. Now, the next thing I need is something called a key, which is a piece of information that I have to keep secret. And what I'm going to do is I dreamed up this key from somewhere, 314-159-265-358. Some of you may recognize that. And now what I'm going to do in order to disguise the message, which is this thing I call plain text, is I'm going to add the key sort of digit by digit. Now instead, you say, well, wait, you're going to add the two numbers? No, I'm going to add them digit by digit. I'm going to add the 9 and the 8, and I get 17. Well, I'm just going to toss everything but the first digit. I'm just going to keep the ones digit. So 9 and 8 is 7. And 1 and 9 is 0, and so I get that. That is a scrambled message. It doesn't mean anything. It certainly can't be converted back to letters. Now, how do I unscramble it? How do I unscramble it? Say again? You subtract the key back. Now notice, so now Dr. Steger has sent this to, I don't know who, you know, the chairman of the Board of Visitors, the rector of the Board of Visitors here, who has asked him this question. It's a question that is continued. He got to get a good answer to this, because if he doesn't have a good answer, his employment may hang in the balance. So he's made it secret. Now, the Board of Visitors chair, the Board of Visitors rector, has this key also. Notice, you have to subtract the key back. So 8 from 7, well, that's 8 from 17, that's 9, and 5 from 6 is 1, and so forth. And look, you get the plain text back. This is a very common method of encryption. It's called additive key. You add in the key digit by digit, and then in order to decrypt, you subtract the key. Now, you get the plain text back. Look what it is. It's the same thing we started with, hokies. That's what he wants to tell the rector of the Board of Visitors. However, some unscrupulous person got in there and compromised the key at the other end and switched it. The key got stolen on its way from Dr. Steger's office to the rector of the Board of Visitors. Got stolen, and somebody changed it. Now, of course, Dr. Steger did this. Of course, he encrypts it in this nice way. But now we have a bad key. Now, you don't know that's a bad key, but you have to trust me, it is. Because if you use this and subtract it off, this is what you get. So there's a real problem. Key management. Public key cryptography was an attempt to solve an ancient problem, which was, how do you deal with key management? You have keys flying all over the place. Now, the one suitcase, two locks business was a situation where Brad had his key, I had my key, and knowledge of how to open Brad's lock gave you no useful information at all on how to open my lock. And about 30 years ago, Whitfield Diffie and Martin Hellman invented something which is now known as the Diffie-Hellman key exchange. And what it does is allow two people to agree on a common key, even though neither one can construct the key without the other's help. And we're going to do that now with communicators. And here are our communicators. The communicators have to have, what are you laughing at? Just for that, you're going to be the first volunteer. You too. Oh. You're going to have to help each other, okay? All right. The communicators can communicate, let's see, who wants to be a volunteer over here on this side? Okay, Corey. All right. Corey and
Jackie, yes.
Jackie. Yeah. Give that to her. She's supposed to. You're going to help him. Okay. Please. All right. Now, the deal is that you can only communicate with each other if the contents of the can are identical. Now, there's a rule about the can. It's got that little slot in the top. You can't take the top off or it'll explode. There'd be a great big hole in this nice building. You can't do that either, okay? Now, I'm going to give you the equipment whereby the contents are M&Ms, okay? Now, so when I tell you so to do, you will open the bag, but don't do it yet. You know the drill. You've not seen it. All right. No, she has to open it.
I do?
Yes, you do. No, you're not going to help him. You're not going to help her. All right. Now I'm going to give you something else. All right. Open the bags. You need that. Did you get it? Who got it first? You did? Great heavens. That was a tie.
Competition.
Well, yeah. Yeah, I've given this talk 39 times, and 37 out of the 39 times the women have opened it first. I don't know what that says. Okay, now, here's what you're going to do. You're going to put some M&Ms of each color in the container, and you are going to record how many of each color she puts in there. No, but don't put too many. We don't have a whole lot of time. Okay. All right? All right. You got to put it through the slot. That's right. Yeah. You're a college professor. You understand these things. Yeah.
Same thing?
Yeah. You can open it a little bit more further.
Okay.
And she's got to write down what you're going to do. Sometimes it's hard to follow instructions. Well, while they're doing this, I want to show you a little bit of the early history of public key cryptography. And actually, it actually goes back to the mythic past of Circe's cave. Circe was a person in the Odyssey who, what did she do? What did Circe do? You remember? Anybody remember what Circe did? I know Dr. Papillon knows. She turned men into swine. Clearly unnecessary. Right. And she had a cave with a secret door. And supposedly the secret of it was you could go through the door on either side if you knew the secret. And she told Odysseus that she knew the secret. So Odysseus would go out to the cave, to the door, and tell her to go in. She'd say she's ready, and he'd say something like, come out the north door or come out the south door. Because she knew the secret, she could get through every time. It sort of looked like this. You know, it looks like that. If she knows the secret, she'll use the right door every time. But if she doesn't know the secret, she has no idea where he's going to be. She has no idea what he's going to say, and so she's got a 50-50 chance of winning, of guessing right. And if she guesses right 20 times in a row, that's a 1 in a million shot. Put it up there, yeah. So anyway, have we got them? Yeah. All of them? Well, as many as I want. Well, all right. How about you? Okay, now. No, just hang on to that. Okay, now we have to get, the cans have to have identical contents. How are we going to do that? Do you know what he put in there? Nope. Do you know what she put in there?
No idea.
How are we going to do it? Repeat it for the studio audience.
Trade cans, and they do the same thing.
Trade cans, and they do the same thing. Isn't that brilliant? This is a Virginia Tech student. I think that's wonderful. All right? Do the same thing you did before. That's why we wrote them down.
The same ones?
The same ones, yes, doctor. That's right, yes. Isn't that fun? Yeah. This is a perfect example of this. This is an emulation of what I call the Diffie-Hellman key exchange, which is a way of exchanging information. Each of you keeps your own information secret. Jackie knows what she put in there, and Corey knows what he put in there, but neither of them knows what the other did, and you cannot reconstruct what the other person did by just knowing what you did and knowing because the actual arithmetic it's a hard problem. Now, I'll explain. A hard problem in arithmetic is something like this. You take two really large prime numbers, numbers that don't have any divisors, like 300-digit prime numbers, multiply them together. That's easy. Well, it's not easy, but it doesn't take long. The hardest part is entering the data. You get a 600-digit number. Now, that's not hard. What's hard is someone hands you a 600-digit number and says it's the product of two of these huge primes. Find the primes. The heat death of the universe is short in comparison to the time it would take you to do this. Are we done? All right, let's see. Okay, now, all right, we got that. And Corey, you've got yours. All right, now, I want an unbiased observer to see if they really did this right. Who's unbiased? You work in the provost's office. You're clearly unbiased. Come on up here. Okay, now we're going to show you. See? We're going to pour these out on here and see that they're all the right colors. Oh dear. Well, hang on a minute. All right, that's not easy to do, is it? No, oops, hello. Oh yeah, all right. Now, so let's separate out the colors, shall we, Mark? Okay. Oh, isn't this fun? You didn't know mathematics could be that much fun, did you? All right, what have we got here? Oh, sorry, yes, right, okay, okay. All right, so what have we here?
These different.
Yeah, they're different. Yeah, they're right. Yeah. All right, so how many greens? You tell me. There.
7.
1, 2, 3, 4, 5, 6, 7 greens. Okay. How many yellows?
3.
3. How many blues?
5.
5. Right. How many chocolate browns?
1.
1. How many oranges?
1.
How many bananas?
1 red.
1 red. Congratulations. You've successfully done the Diffie-Hellman key exchange. These are examples of public key cryptography.
Wait, but we can't open it because we don't know what it is, right?
That's right. You don't know. But the point is you both have the contents identical and you can communicate with each other, despite the fact that you have nothing to say to each other. But you should.
Once they're identical. This is the new key.
This is the new key.
And you both share it.
And you have you're sharing the key. And the problem of transporting a key across a network that might not be secure has been solved. Now that raises a whole, thank you very much. I'm sorry. That raises another bunch of issues. But at the time, this solved a problem that really was very thorny. And it was all done with simple arithmetic. Nothing complicated. Now, what do you do with the M&Ms? You eat? No, you don't give them back. That's the only time anybody's ever said give them back. College professors. What do you do with them, Corey? That's right. Okay.